Head-mounted displays are becoming increasingly popular, but they often cause visual discomfort and even nausea. In this paper, we study how display protocols in different HMD designs interact with visual discomfort. We design a carefully calibrated measurement device and perform 2 studies to determine which protocols have the largest effect on discomfort. Vergence is the rotation of the eyes to fixate an object and maintain a single fused image. Accommodation is the adjustment of the eye's lens power to maintain a sharp image. Vergence and accommodation are neurally coupled, which helps maintain a fused sharp image. In the real world, vergence and accommodation are matched to the distance of the object of fixation. The left window is a zoomed-in view of the retinal image. As the eyes accommodate to the cube, natural depth of field blur is generated on the retina for the rest of the scene. In HMDs, no blur is generated on the retina. The virtual scene appears at different distances, but light comes from a fixed distance of the display. Thus, vergence and accommodation are generally not matched because the eyes accommodate to the fixed distance of the display screen, while converging to the varying distance of virtual objects. This vergence accommodation or VA conflict causes visual discomfort because such a conflict requires the viewer to fight against the natural coupling between vergence and accommodation. We examine 3 display configurations that have been proposed to match accommodation to vergence in the hope of minimizing discomfort, but they have never been rigorously evaluated. Gaze-contingent depth of field blur, focus adjustable lenses, and Monovision. To evaluate the proposed configurations, we need to answer 2 questions. Do they drive accommodation to the distance of the simulated object? And if they do they improve comfort? Gaze-contingent depth of field or DOF blur requires natural blur on the retina as can be seen on the left panel. The blur is consistent with the vergence distance. Focus adjustable lenses combined with gaze-contingent DOF blur achieve natural blur on the retina and should also help accommodation because they change the focal distance of the screen. Monovision attempts to force accommodation to alternate between 2 fixed distances. The goal is to reduce the VA conflict, since accommodation distance should be closer to vergence distance for a larger proportion of time. See how the retinal blur flips between the 2 eyes. We created a device to measure accommodation. It is a splittable HMD that can be used with an autorefractor, a device that measures accommodation. We mounted the separable display panel and the lens assembly on the autorefractor. The participant fixated the stimuli while the autorefractor measured accommodation. We now show the results of our accommodation study. On the left, we can see a data recording from the changing lens condition. The brown-colored trace is the stimulus in time as it came nearer and went farther. The cyan color trace is the accommodation measurement. We fit the sinusoid wave to the accommodation data, shown in purple. In this case, the fitted sinusoid closely matches the stimulus. The right panel shows a case in which accommodation did not match the stimulus well. This is the fixed lens condition for the same subject. The ratio of the fitted sinusoid to the stimulus sinusoid is the gain of accommodation. Here, gain is represented by the abscissa, and the conditions are shown on the ordinate. For the binocular experiments, the gains in the fixed lens condition are low, while gains in the changing lens conditions are higher. The same happens for the monocular conditions. For monovision, the stimulus and expected response are shown on the left. The stimulus measurement and fitted response are shown on the right. Accommodative gain is quite low in the monovision condition. The gains for all subjects for the monovision conditions are shown here. Our results show that gaze-contingent DOF blur does not drive accommodation to vergence distance. So the VA conflict can be large. Focus adjustable lenses combined with gaze-contingent DOF blur successfully drive accommodation to vergence distance. So the VA conflict is minimized. Monovision does not drive accommodation as intended. Accommodation distance is flipping in time. We can predict from the accommodation data that the changing lens condition would be the most comfortable and that the monovision condition would be the least comfortable. We next evaluated these predictions by performing a discomfort study. The subject did a visual task in the HMD for 2 protocols, presented in random order. This involved the tumbling E. At the end of a session, they compared their symptoms in one protocol to their symptoms in the baseline fixed lens condition. Our results indicated a slight preference for DOF rendering over pinhole rendering, a strong preference for changing lens over fixed lens, and a clear preference against monovision. Among the conditions we examined, the most effective way to improve comfort in head-mounted displays is to incorporate focus-adjustable lenses.